Good morning, good morning, good. Hey, how we doing? It is a beautiful Thursday morning here in cloudy and gloomy Rochester, New York. It's going to be 73 degrees today, which is like a blessing, which never happens here. But it's going to be cloudy, not sunny. Chance of rain, maybe thunderstorms, It's always got to poop on our dreams, always. Anyways, welcome. We are going to begin the Algebra 2 Common Core exam for January 2017. All right. There will be 5 videos. This is the first one, and it will cover problems 1 through 8. And if you've followed me for the June and August 2016 exams, you'll notice that what I like to do is color coordinate problems into 4 different categories. This test in particular, you are going to see some problems where the problem number is highlighted in this orange. That would be something I classify as an algebra type problem, heavy algebra. Highlighted in blue will be data and stats. Yellow is trig or an exponential. And 7 of these problems fall into what I would highlight under purple as in like miscellaneous. It's not those 3 other groups. And most tests I've gone over, I've got to go over the more recent tests like 2019 and maybe the end of 2018 still. But most of them have these kind of similar numbers. 18 are going to be algebra on this test, 6 data and stats, 6 trig and exponential, and 7 fall under miscellaneous. And within 2 to 3 numbers, these kind of hold true within an error of 2 to 3. So maybe instead of 18, it might go down to 15 and so forth. But let's get started, shall we? Bang. Okay, part 1, this is the multiple choice. There are 24 questions. They each get 2 points, 2 credits per question. A lot of kids, I say this all the time, I love me multiple choice because the answer is there. I like multiple choice, but I don't like it because there is no partial credit. You can be 99% correct and make 1 minor mistake, and you get nothing. Nothing! You get nothing. In fact, you can be right with your work, and you could just accidentally bubble in the wrong answer, wrong choice, and guess what? 0, zip, nada. So please pay attention to what you're doing. Use that calculator when you can, and let's get started. All right. Number 1, this is yellow, so I would classify this as trig or exponentials, and this is obviously trig because we see the sine function. Relative to the graph of y equals 3 sine of x, what is the shift? Okay, the movement of the graph. Yeah. So compared to this, what does this do? Okay, so when I look at my equations, I see one major difference. Okay, there's a 3 here, there's a 3 here. There's an x here, there's an x here. The only difference is we are adding pi plus 3 inside the parentheses. Rule of thumb, and I will use sine here. If I have anything, we'll call that sine of x. If I add or subtract inside the parentheses, I will call this h. And if I add or subtract outside the parentheses, I will call this v. H represents horizontal movement, and V represents vertical movement, up and down. Okay, H is left and right, horizontal. V is up and down. All right, vertical. If I add outside, I move up. If I subtract outside, I move down. Okay, whatever number that is. All right, so if I added 3 to the outside, my graph would move up 3. If I subtracted 2 on the outside, I would move down 2. All right, that makes sense. The inside always works in the opposite fashion when it comes to graphs. Okay, if I add on the inside, I don't move to the right because that's where the positives are on the x-axis, correct? If I add on the inside, I'm moving left. If I subtract on the inside, I move right. Okay, so this is what we're dealing with. We are adding and subtracting something on the inside. Since I'm adding, that tells me I'm going to move to the left this many units, pi over 3. All right, so all you really need to do is know the rules, and you're going to answer this very, very quickly. I'm moving left pi over 3 units. Now, if I had a calculator, I could graph this in y1. I can graph this in y2, and I could take a look at how it moves, the graph. Or I could look at the table and see the movement. But it's a lot easier to just know your rules, what I have written here. This really helps. All right? Number 2. All right, another yellow. Wow, it's rare that we start with 2 trig or exponentials. Number 1 was trig, and number 2 is an exponential problem. A rabbit population doubles every 4 weeks. There are currently 5 rabbits in a restricted area. If t represents the time in weeks, okay, and p of t is the population of the rabbits with respect to time, about how many rabbits will there be in 98 days? All right. So growth and decay, population, okay, it doubles every 4 weeks. All right. So my end amount is going to equal my initial amount, ab to the x, we'll call it, because this is an exponential. All right. It doubles every 4 weeks. So the inside, I'm going to multiply it times 2 if it doubles. And my time is going to be in 4 weeks, okay? This rate makes this t represent 4 weeks. All right? That's important to understand. Now, what does it say? There are currently 5 rabbits, okay? This is our starting value. 5. About how many rabbits will there be? So we're solving for A. In 98 days. Okay, time out. This freaks me out right here. How come? I have weeks here, so let's convert 98 days to weeks. If I have 98 days, to make that weeks, there are 7 days in a week, right? So how many 7-day increments go in there? That's actually 14. So 98 days equals 14 weeks. So let's say we're just going to figure out how many rabbits there'll be in 14 weeks, because my t is already in weeks. All right? But here's what we need to do. Ready? My exponent is in 4-week increments. Okay, t actually equals 4 weeks. Not 1 week. 4 weeks. Okay, I want to make t represent 1 week, and then I could just put the number in. I could put 14 in for weeks. You see how they want this in 14 weeks? So I want my variable to represent 1 week. How come? So then I could just throw the number 14 in there. So how do I make t equal 1 week? Well, how do I make the right side equal 1 week? I divide it by 4. So now that's 1 week, right? What I do to one side, I have to do to the other. So t over 4 represents 1 week. You really need to understand that. So 5 times 2. Now I have t over 4. Now this is in 1 week. It's no longer 4 weeks like it was here. Now it's 1 week. 14 weeks later, how many will we have? Now I can throw 14 in for this t, because t represents 1 week. I want 14 1 weeks, so to speak. So 5 times 2 to the 14 over 4. What does that equal? Good thing we have a calculator, and if it would pop up, there it is. Turn this on, mine. There it is. I take 5, and I multiply it times 2, raised to the 14 divided by 4. Pachow! 56.568. Let's call it 56.6. That is roughly 56.6. Is that 56.6? It is. Weird. All right. They say about how many rabbits? Mister, I don't see 57, because this is about 56. This is population, okay? This rabbit, okay, might be pregnant and might be 60% of the way through her pregnancy. That rabbit doesn't count in the population until it's born, okay? But they say about. I hope you would circle 56 and not say, well, it's about 3,688, because I came up with 56.6. That makes no sense. Come on, use some logic, man. This is math. Number 3, algebra. Great. I love it. When factored completely, m to the 5th plus m cubed, or, yeah, that's right, plus m cubed, minus 6m is equivalent to what? Calculator alert. If you wanted to, you can put this in y1, and you can try, let's say, this in y2. If they are equal or equivalent, their graphs will be the same. If number 1 doesn't have the same graph, then I put this into y2. If they are equal, their graphs will be exactly the same, okay? But be careful. You see this word completely? You might have 2 of these things where the graphs are the same. One is a factored version. The other is factored, but factored completely. Meaning, I see this right here, and I know this can be factored again. This might be the same as what we have here in y1, okay? But I guarantee you there's another one that is exactly the same graph as well. One is factored completely, okay? So let's just go ahead and factor this algebraically because factoring is important. First thing I want to do, they all have an m. So I'm going to take an m out. All right, that leaves me m to the 4th plus m squared minus 6. All right, I have my m. And look at that. That's the same thing as here. Okay, so don't just circle that. This is factored, but it is not factored completely. Booty cheek time. Ba-da-da-da-da. You might be saying, Visca, I only know when this is a 2 and this is a 1. Okay, let's do this in red. If we had a 2 and a 1, I'd have m to the power of 1, m to the power of 1, right? What multiplies to negative 6 that adds to positive 1? Well, it's plus 3 and minus 2. That's factored. But we don't have that, do we? Okay, notice that when we have 2, and then the exponent in the middle is half of that, whatever that exponent is, I put here. Okay, so let's go back to our problem. We have 4 and 2, right? Well, 4. 2 is half of 4. So I'm going to put 2 here. And that's your answer. That's it. Literally, quite literally. And that, my friends, is choice 4. So if we graph this, 3 and 4 both have the same graph as what's in our problem originally right here. Okay, this is the same graph as both of these, but one of them is factored and one of them is factored completely. Choice 4 is factored completely. Lordy, lordy. 3 out of the first 4 problems fall under the trig and exponential content area. This one is such a gimme, it's sickening. If sine squared of 32 plus cosine squared of some value m equals 1, then m equals what? This is a rule, okay? It is the trig rule for the Pythagorean theorem. Sine squared of x plus cosine squared of x equals 1. Whatever value this is, if this is the same, you get 1. So if this is 32, this has to be 32. That's it, point blank. Is there another way you can use the calculator for this, Visca? Absolutely. I can take 32 and plug it in for m. I can put this in the calculator and hit enter. If it gives me 1, that's the answer. Just plug these values in for m and see which one would give you 1. Guess what? It's 32 degrees, choice 1. Oh, that was a layup. Number 5, what is the solution to the system of equations y equals 3x minus 2 and y equals g of x, where g of x is defined by the function below? So they don't give us an equation for g of x, so I can't just put 2 equations in the calculator here, all right? But what I can do is I can graph this. If you need to put that in y1 and look at the table, go ahead and plot those points. This is algebra 2. You should know how to graph this. This is my y-intercept, -2, which is right here. And my slope is 3, which means I go up 3 over 1. 1, 2, 3 over 1. Oh, that's one of the points. 1, 2, 3 over 1. 1, 2, 3 over 1. I don't know, maybe right there. Okay. 1, 2, 3 over 1, and it's going to continue. Sorry. Like this. All right. Now, you can answer the problem. Here are all our choices over here. By looking at this point of intersection right here. That's at 1, 1. Okay, that's the coordinate 1, 1. There's only one option that has 1 and 1. That is choice 4. You might say to yourself, though, but it looks like it only crosses once. Let me explain something to you. You see these arrowheads? That means this goes on forever. Okay, this goes on forever. So at some point, the green line and the black line will cross a second time. It's just not really on your screen. And that would be at 6 and 16. Okay, 1, 2, 3, 4, 5, 6. 6 is right here. Now that's actually really accurate where I drew those. That would have a height of 16. All right? So they would cross a second time. Right? Did you need to know that? No. The only thing you needed to know was this is definitely an answer. Here's the only solution or choice that has that answer. Good. Easy. Number 6. This is a data and stats problem. Welcome to the party, my friend. Which statement about statistical analysis is false? 3 of these are going to be true. Do not circle the first true response. All right? Italicized does not mean invisible. I say that all the time. But let's take a look at these things. Some of these things, because we really don't, drill this type of content in class, experiments can suggest patterns in relationships and so forth. It's almost like common sense, and I really don't like these problems, but here's what I'm going to do. I'm going to look at all 4 of these responses, figure out which ones are true and which ones may or may not be true, which ones may or may not be false, and kind of do a process of elimination. Okay, first of all, you'll notice that there are 2 types of statistical analysis in my responses. They have experiments. Okay, 1 and 2 mention experiments. And 3 and 4 mention observational studies. Okay, let's first explain the difference between the 2. An experiment is something that you kind of have control over, and you typically interject something in an experiment. Okay, I'm going to experiment. I'm going to see what happens if I drink soda every day for a month straight for breakfast, lunch, and dinner. That's an experiment because you're taking something, you're injecting cola into your diet, so to speak. That's an experiment. Think about it this way, you're putting something in. All right. Observational studies, you don't do anything, you just watch. Okay, like that pervert that stares through your living room window every once in a while. I'm just kidding, I'm joking. An observational study is, okay, I'm just going to sit here and relax, and I'm going to go into someone else's classroom, and I'm just going to sit in the back and just watch. I'm not going to get up and teach someone else's class. I'm going to watch them teach. I'm not going to help them at all. I'm just going to sit in the back and observe. That's an observational study. I do not put anything in. Okay? So let's look at our responses. Experiments can suggest patterns and relationships in data. Absolutely. I know that's true. Okay? Patterns and relationships. Types of things, things that happen commonly and the relationships between certain things. Okay, yeah. Okay. 2, experiments can determine cause and effect. Absolutely. If I sit in the back of a classroom and I throw a $100 bill on the floor, I'm going to see an effect from the cause of me throwing that money on there. There'll be some black eyes and some broken teeth. All right, that's true. Observational studies can determine cause and effect. I don't think that one is necessarily true. Cause is me creating something. I'm creating a cause to see an effect. Observation typically does not do that. Nah, that one might be the false one. And number 4, observational studies can suggest patterns in relationships. Absolutely. If I sit in the back of the class, maybe I can see, well, the kids that work together tend to do better. That's a pattern. And there's a relationship created by kids working together. Okay, so this can definitely be true. I know this is the only one that I don't think can be true. This can definitely be false, okay? The other three I know for a fact are true. And if I look at the answer key, number 3 is absolutely the answer, and that's what I would go with. And that's how I would suggest answering any type of question like this. I really haven't seen a question like this recently, but who knows? Maybe it'll pop up again. All right? Okay, here, children. Okay. The expression m squared over m to the 1/3 all raised to the power of 1/2 is equivalent to what? All right, here we go, people. You can do this one of 2 ways. And this is why I'm thinking. I can handle what's in the parentheses first, then apply my negative 1/2 exponent, or I can apply the negative 1/2 exponent to both of these and simplify my fraction afterward. I will simplify what's in parentheses first. And this is really just a question that tests you on your knowledge of rules of exponents. Whenever I divide, let's just look at these 2 things here inside the parentheses. Whenever I divide 2 common bases with exponents, I subtract the exponents. So really what's in parentheses here is m 2 minus 1/3. That's raised to the negative 1/2. So let's simplify this even more so we have 1 exponent. 2 minus 1/3. Well, I really should get the number 2 to become a fraction with a 3 in the bottom. 6 over 3. That's the same thing as 2 minus 1/3 is 5 over 3. All right. So I have m to the 5/3 raised to the negative 1/2. Now let's apply our negative 1/2 on the outside. All right. When I have an exponent raised to an exponent, I multiply. So that's m, positive times a negative is negative, 5/6. All right. Now, anytime I have a negative exponent, I need to flip it, which means this is 1 in front of here, right? I have 1 over m to the 5/6. Well, I know it can't be 1 or 3 because it's got to be a fraction with a 1 on top. And there's a rule I say top down, bottom out. I'm going to turn this into a radical. You'll notice that both of these answers, 2 and 4, have a radical sign in them. My m stays here. The top just slides down, my 5. The bottom pops out of the radical. That becomes my root. Top down, bottom out. Kids love that saying and they remember it. The problem is, if you have to explain the process, you really shouldn't explain top down, bottom out. You should really say the numerator, which is the 5, comes down and becomes the exponent for the m. The bottom, or the denominator, pops out and becomes the root. And that, my friends, is choice 2. Wow, we're making some good time here. Some easy problems. And that was number 7. Number 8, I classify this as a miscellaneous. I mean, someone might say it's algebra. It's finding the inverse of a function, y equals log base 3 of x. In order to find the inverse, and yes, there's a way to do this in the calculator, but in order to find the inverse, because if this, I'm going to show you algebraically, if this was a short answer problem, you'd have to know how to do this. Okay. In order to find the inverse, you just switch x and y, literally, and then solve for y. Okay, you switch your x and y and solve for y. So I am quite literally going to take my x and move that to where my y is. And I'm going to take my y and put that where the x is. So if I rewrite this, I now have, okay, this is going to become my y, and this is going to become my x. So I'm going to say the log base 3 of y equals x. Okay, so now I've got to figure out how to get this in terms of y equals now. All right, and whatever that is, that's my inverse. Okay, your rules for log. Quick review. If I have log base 5 of 25, that equals 2. Okay, I'm just going to put some numbers in here. Log is like saying what power or what exponent of 5 gives you 25? Well, 5 squared. Meaning, if I wanted to, I can drop this log, and I can take this value and switch this. And I can say 5 squared is 25. You see what I did there? I'm going to take that same logic and apply it here. I'm going to drop this log by switching this value and this value. So I'm going to say 3 to the power of x equals y. I just solved for y. Here it is. So this is my inverse. That would be choice 3. Now, you had told me, or you're probably asking me because I told you, you can do this in the calculator. So you're saying, Visca, how do we do this in the calculator? In the calculator, on the graph, when you have an inverse, it's like a reflection over the line y equals x. Okay? So, if we did this right, if I graphed this in y1, and I graphed this in y2, this blue that I highlighted will look like a complete and perfect reflection of what I highlighted in yellow in y1. But it would reflect over the line y equals x. And I'm going to show you that because we have time here. We went through these first 8 problems rather quickly. On. There we go. Clear this out. Let's go to y equals. Yeah, that's right there. I'm going to put y equals into y1. We'll put log. I'm going to put this one into y1. Okay? Bang. So I'm going to say, I don't want to hit log because I can't put a base here. Okay? I can't put a base there. All right? So I've got to clear that out. Log base, if you hit math, a number, or is it just math down? Log base, it's A. I don't like doing that. I like hitting, you know how you can hit alpha y equals and it can give you fractions? I like to hit alpha window and look at choice 5. It's log. I just like the shortcut menus. Bam. Log base 3 of x. Now, let's graph this. And I'm going to have this detached thing right here. If I graph this, this is what it looks like right here. You get this thing. I'm going to do this in red. It looks kind of like this. Okay? If I reflect this across y equals x, that's the graph of the inverse. So let me go here. Just so that you see what y equals x is, I'm going to say y equals x. Now I'm going to graph that. There's y equals x. I will do this in blue. Yep. Now, if I did this right, okay, and these reflection points, this would reflect here, this would reflect here, this would reflect here, this would reflect here, this would reflect here. Okay, so the graph of the inverse would look something like this. A perfect reflection, okay, a perfect reflection right across y equals x. Let's not forget y equals x. This is the line that my red graph will be reflecting over, and it should kind of look like what that green thing is, okay? So the only graph we have that should look like that should be choice 3, our answer, y equals 3 to the x, all right? So if I go here, yep, bang, y, that's here, here. Let's go to y equals, and I know those marker things are still there, and I would have that, I have that. I'm going to put 3 to the x here, 3 raised to the x. If I graph that, oh, look at that. My green thing's a little bit off. Sorry. Right there should look like. But that is a perfect reflection. Okay? If I take my original function and I graph it and I reflect it over y equals x, that's the graph of the inverse. The other 3 graphs would not look anything like that. They would not look like a reflection. Again, the reflection has to be across this line, y equals x. Here's the original function. This is the inverse. That's -1. That means inverse, okay? So if I take this and I reflect it over my thick blue line, it should look like this. All right? And it does. Did you need to know that? No. Is it helpful in case you don't know how to do this algebraically? Yeah. First video done, my friends. I will see you back here for 9 through, I don't know, 16 or 17. 9, 10, 11, 12, 13, 14, 15, 16. 16, 9 through 16. See you then, part 2. See ya. Study, because you got this.